Laurent's theorem, lesson 4. Before starting the examples, we are having some remarks given over here which are very important. So first one is singularity. What do you mean by singularity? If fz is not analytic at z0, then z0 is called singularity of fz. Right? So the points where the function is not analytic, those points are called the singularities of fz. Second, if the series is uniformly convergent and each term of the series is continuous, we say that then some function is continuous. So to prove some function to be continuous, we need to prove the series to be uniformly convergent. Then third one is summation n going from 1 to infinity. 1 over n square is equal to, its value is pi by 6. This you need to remark and note. So the example, let fz is equal to infinite sum on z square over 4 plus n square z square. Show that function is finite, first thing, and continuous for all real values of z. Second thing, we have to show that this function is finite and some function to be continuous. Third, fz cannot be expanded in a Maclaurin series. This we also will need to show. So the first thing is this. Second, continuity. And third, fz cannot be expanded in Maclaurin series. Fourth, show that fz possesses Lorentz expansion valid in a succession of ring spaces. So these four things we have to show. So the first one is, show that fz is finite. That means we have to bring this function to be less than some real number, right? Let's check. So for the solution, let fz is equal to, which is given to us, n going from 1 to infinity, z square over 4 plus n square z square. Now for all real values of z, we have this function is obviously strictly greater than 0, right? Let me write in the next page. Which is equal to summation n going from 1 to infinity z square over 4 plus n square z square. This is less than, yes, just think about the denominator. If I skip the denominator 4, which is positive, so this will be less than z square over n square z square. Right? This fraction will be greater than previous one, which is equal to summation n going from 1 to infinity. You cancel z square and get 1 over n square. And from the remark, summation n going from 1 to infinity 1 over n square is pi square by 6. This is from the remark. So we show that this function is lying between, the value is lying between 0 and pi square by 6. So this is a finite function, right? Hence fz is finite for all z. Now next, again since, but yes, real values of z. For all real values of z. Important. Again, since summation n going from 1 to infinity z square over 4 plus n square z square. Now we need to show that the given sum function is continuous. For that we need to prove the function to be uniformly convergent. So again, you see this sum is equal to, this is less than, again you have to check the denominator. Can I write this is as less than 1 over n square? Yes, of course. The denominator is positive. I am skipping the term 4. And again z square cancel. Just the same term I getting this over here. And we know that by p-test, this 1 over n the power p by p-test, this is convergent, right? Because p is greater than 1, that is 2. So, and summation n going from 1 to infinity 1 over n square is convergent. So by Weierstrass test, we are using the Weierstrass test. The series summation n going from 1 to infinity z square over 4 plus n square z square converges uniformly. Also, each term of the series is continuous. Therefore, the sum function fz is continuous for all z, the second remark, right? Okay, now to prove that the function cannot be expanded in Maclaurin series. Now for all complex values of z, we see that each term of the series is not analytic at, yes, z equal to plus minus 2 iota by n, right? At this point the function is not defined, so the function is not analytic at z equal to plus minus 2 iota by n, where n is from 1 to 3. Now again from the remark we see that the points where the function is not analytic, that points are the singularities, right? So the function is not analytic at plus minus 2 iota by n. Thus, fz possesses singularities in every neighborhood of 0. See the figure. Whenever the function possessing the singularities about the neighborhood, in the neighborhood of 0, there are so many singularities. What are the singularities? See, put n equal to 1, I am having plus minus 2 iota. Put n equal to 2, I will be having plus minus iota. Put n equal to 3, will be having 2 iota over 3. So the denominator is increasing. So likewise going on, we reach plus minus 2 iota over n. Then plus minus 2 iota over n plus 1. Just check this figure. This is the point 0 having the neighborhood. There are so many neighborhoods of 0 and we are having so many singularities in every neighborhood of 0, right? In this we are having plus minus 2 iota over n plus 1. Then we are having the singularity. If we check this as a neighborhood of 0, we are having plus minus 2 iota by n, right? So there are so many rings formed, right? Having so many singularities. So whenever, if every neighborhood of 0 possessing so many singularities, we say that function cannot be expanded in Maclaurin series about neighborhood of 0. That's why here it is written, thus fz possesses singularities in every neighborhood of 0, hence fz cannot be expanded in a Maclaurin series about the 0, about the origin, right? Next. Since fz is analytic in the ring-shaped region, yes. See, 2 iota over n plus minus and plus minus 2 iota over n plus 1. This is your ring-shaped region. Can we say that function is analytic in this? Yes, the function is analytic in this. Now, since function is analytic in the ring-shaped region, mod z lying between 2 over n plus 1 less than 2 by n for all n equal to 1 to 3. Hence, fz possesses Lorentz expression valid in a succession of ring spaces defined by mod z lying between 2 over n plus 1 and 2 by n, where n is 1, 2, 3, so on. So here ends up the example. Thank you for watching this video.